In this video, we'll wrap up this exercise on Euler's method with Part C. Part C says use the integral from 3 to 3.1 of f prime of x to evaluate f of 3.1. So what we've seen here is in Part A, we found the equation of the tangent line, and we did a tangent line approximation of the original function to find f of 3.1, or to approximate f of 3.1. Second of all, we used Euler's method to approximate 3.1, and you can see that the values that we got back for the tangent line approximation, we got 6.234. For Euler's method, we got a value of 6.236. Both of them are fairly close to each other, fairly close approximations. Now, we're going to be able to actually find the value of f of 3.1 by using an integral. And the way this is going to happen is as follows. Well, we know from the fundamental theorem of calculus that, by definition, the integral from 3 to 3.1 of f prime of x dx is simply the antiderivative of f prime of x, which is f of x, evaluated at the upper limit, minus the antiderivative evaluated at the lower limit. Now, we know that f of 3 is 6, and we can use our calculator to find the definite integral from 3 to 3.1 of f prime of x dx. So 6 plus integral from 3 to 3.1 of f prime of x dx is going to equal f of 3.1. And we're going to need our calculator now to do that. So you recall that we already have our derivative, 1 plus e to the x quantity divided by x squared, in the calculator. We go to graph, and we can find the definite integral. Second, trace, option 7, lower limit 3, upper limit 3.1, and that tells us that the definite integral we're looking for is 0.2377, or 0.2378. Added to 6 is going to give us 6.2378. And rounded to 3 decimal places, since this is a final answer, we would need 6.238. Now I'm going to close the calculator down, and we're going to take a look at this. Again, we have just used, the great thing about this problem is we used a tangent line approximation, we used an Euler's method to approximate f of 3.1, and we used a definite integral to give the exact value of f of 3.1. And we confirmed the fact that because the first and second derivatives were both positive, we were increasing and concave up, and so the tangent line at that point would fall below the curve, and so any approximations on it or from it would under approximate the actual value, and we can see that that is actually true. So with the tangent line approximation, we got 6.234. With Euler's method, we got a better but still under approximating 6.236, and the actual value we've seen is 6.238. Now with the Euler's method part, we only checked the first and second derivative at x equals 3. And using Euler's method, we also found that the first derivative at 3.05 was also positive. Now, if we had checked the second derivative at 3.05 and saw that it was also positive, which I believe it will be, then we can say that because at 3 and at 3.05, the first and second derivatives are both positive, so therefore any tangent lines at those points there would under approximate the curve. I hope that makes sense. And this is actually a very cool problem showing different ways of approximating and finding exact values of f of 3.1. So we'll stop that here and go on to another problem.